Hey everyone, Miss Beller here. I know that we're asking you to watch lots of videos lately, so I'll try to go through this quickly. But this is just kind of an update video on how we're going to grade for all these review assignments. And then just tying some loose strings on the acid-base mini lessons, electrochem mini lesson, and the equilibrium mini lesson. Wow, I look sweaty and hot. I was just pulling weeds. It's 80 degrees. Anyways, grades updates for you. So a couple of things. We created a new category called remote learning, but really it's everything from your mock exam onward. So your mock exam, your mini lesson that you're making, your participation in the discussion, anything else we come up with, whether it's assignments or a second mock exam, all of that will go in there. It's weighted at 0, so it's not helping or hurting your grade. What we're going to do is we are going to give you extra credit points each week based off your participation in the discussions and any other assignments. You will also receive extra credit for your mini lesson, and you will receive extra credit for your mock exam. If you got a 5 on the mock exam, you will have 15 extra credit points. If you got a 3, 13. If you got a 1, 11. So you should already see that in your formative category. And then if you did your review for the mock exam, you can do corrections for 3 more extra credit points on that first mock exam. But essentially, at this point, the only way to change your grade is 1, if you're missing anything, talk to your teacher, try to make up any missings from earlier this semester. But 2, working and getting some extra credit points in that formative category based off the review. All right, first off, I know I'm just speaking for my class, but Char said the same. The mini lessons so far have been awesome, so please do not think of us going over extra information here as you did a terrible job. The mini lessons are meant to be an overview to remind your classmates of what maybe they need to go back and study more, kind of trigger their memory of what was hard in the unit, what was in the unit, and also help them make their one-pager. So we are tying up any loose ends either you didn't cover in the video or we think we need to go a little more in depth. Not that you did a bad job, you covered what you needed to cover. We're just trying to pull it all together. Okay, so you need to know what the strong acids are. I know this was in Grace's video in my class, but I want to reiterate, put those on your one-pager. Strong acids are considered strong because they break apart 100%. So the H plus breaks apart from the Cl 100% of the time. We are not really at this equilibrium at all. It goes to completion. I also recommend putting the strong bases on your one-pager, but same idea. These guys break apart 100% of the time into the cation, the positive ion, and then the negative OH, the hydroxide. So acid and base reactions are fair game for this year's AP exam. So I'm talking about when I mix an acid and mix a base together, which is a typical titration problem. So we have potassium hydroxide titrated with nitric acid. So we have KOH, that's our potassium hydroxide, that is one of my strong bases, and HNO3 is nitric acid, that's a strong acid. You're going to do a double replacement, so this H is going to go with the OH, the K is going to go with the NO3. You always have water, so HOH is the same as H2O, always a product, and then whatever's left, we have K and NO3, we crisscross those, and we use solubility rules to decide if this is solid or aqueous. So in this case, it is aqueous. NO3 is always soluble. So we know that strong bases and strong acids break apart 100%. So I'm going to split this into the ions K plus, OH minus, H plus, NO3 minus, and then my products, we can't break apart liquid, so H2O liquid, and this is soluble, so it's aqueous based off solubility rule, so K plus and NO3 minus. I cross off K plus, NO3 minus, my spectators. Notice when you have a strong base added to a strong acid, the net ionic equation is always, always, always OH minus plus H plus makes water, H2O. Here's the same thing in Charvella's handwriting. Notice you pull out the water, but if you like Char's handwriting better, there you go. All right, what if they are not both strong? So in this case, rubidium hydroxide is a strong base, but acetic acid, HC2H3O2, is a weak acid. Well, notice we still pull out the water, right? H goes with OH, RB goes with the acetate polyatomic. This acetate polyatomic is aqueous. The strong base we can break apart into Rb plus and OH minus, but a weak acid, even though it says aqueous, stays together in the net ionic. And then this guy, because it's aqueous, would break apart into Rb and the acetate. The Rb is aqueous on both sides, but I cannot cancel out the C2H3O2 minus because on this side it's the ion, on this side it's the weak acid. And then again, we just refresh, what do acids do? They give away H plus, so that H goes over here, which is why we make the water. And what do bases do? They take the OH. So this is a base, this is my acid. Strong base, weak acid, we're always gonna be left with a conjugate. Here's kind of a weird one. We have a strong acid with a weak base. So we can break apart the strong acid, not the weak base. What do acids do? They give H pluses. So we are going to be left with just Br minus, and then this ammonia becomes NH4 plus, right? When it gains in a hydrogen, it gets a plus charge. So we have H plus plus NH3 makes NH4 plus. Those Brs are able to cancel because the strong acid broke up. So what we just looked at when we added an acid base, whether they were strong or weak, those were called neutralization reactions, or those are the reactions that happen when you do an acid-base titration. But I do want to circle back. We talked about the strong acids. What makes a strong acid strong is that if we did an ice table, right, the breaking apart into H plus and A minus, let's say I had 1 molar of this, none of this to start, minus X, plus X, plus X. What makes an acid strong is that this breaks apart into 1 molar H plus and 1 molar A minus. If an acid is weak, so we'll say strong. If an acid is weak, this will maybe break, maybe we have like 0.97. This breaks into 0.03. Where's my eraser? Right? Less than 5%, only 3% of this actually split apart. Most of it stays as HA, only a tiny, tiny bit broke off, right? So we're left with mostly the same concentration, a tiny bit of H plus, a tiny bit of A minus. So a weak acid, only a small portion of the H plus breaks off. A strong acid, 100% of the acid breaks down. All right, lab week labs are fair game. We did 4 labs in 4 class periods. And so honestly, I'm hoping that lab week questions are on there because you guys rocked this. So the first lab is you standardize NaOH with KHP, meaning we were trying to make roughly 0.1 molar NaOH, but we wanted to know exactly what it was. So could we have taken grams to moles divided by liters? Absolutely. But we wanted to we did a titration to be absolutely certain, was it 0.1 molar, was it 0.099 molar, like exactly where we were at. So you can read through the steps, but the main idea over and over is moles of acid equals moles of base at the color change, at the equivalence point. And once you know moles of the unknown, you can pretty much do anything. All right, so as a class, we had an average of the NaOH. This might have been from a couple years ago, but we'll roll with me here. So we had the known concentration, the exact concentration of NaOH, and then we used a mystery acid. It was a solid, so you massed out 0.20 grams, or roughly whatever it was, you wrote it down, and we dissolved that in some water, and we added phenolphthalein as an indicator. And so then we did our titration. When it turned a light pink, we were able to say whatever volume of the base using correct sig figs was required in liters, and then our molarity we can solve for moles. That was moles of NaOH, and we know that equals moles of acid. And then we wanted to find the molar mass, so we know grams divided by moles, grams per mole is molar mass. So if we take 0.2 grams divided by whatever the moles were, that's how we were able to find the molar mass, and we use these as our options and pick the closest one. Same process, we wanted to find percent acetic acid in vinegar, so we added 3 grams of vinegar inside the flask, add some water so it swirled nicely, did our titration with the phenolphthalein. When the color change happened, we had a volume of the base, and so we did liters times the molarity. That gave us moles, and hopefully you see the pattern, moles of base equals moles of acid at equivalence. So then we could go from moles of acetic acid, which we had the formula of, to grams of acetic acid. And then to find percent, we took grams of acetic acid divided by the 3 grams of vinegar times 100. And I'm not going to repeat all of this same process. You can read through it with mustard, except I just want to point out moles of base equals moles of acid at the equivalence point. Whoops. So in my class, Gracie did the electrochem lesson, and she added a little bit of extra stuff. So I just want, again, it was totally fine and I think useful information, but her lesson 3, so if you're in my class, what Gracie called lesson 3 will not be on the AP exam this year. If you already put it on your one pager, don't worry about it. But here's what will be on the AP exam in terms of electrochem. Can you assign oxidation numbers? If there's a balanced equation, can you determine what is oxidized and what is reduced? Can you determine the oxidation or the oxidizing agent and the reducing agent? Can you identify a reaction as a redox? So meaning when you assign oxidation numbers, you notice that one element is oxidized and one is reduced. Can you balance a redox reaction in acidic conditions? Can you balance in basic conditions? One main idea that you might want to add to your one pager, when a redox reaction is balanced, matter, so the elements are balanced, that's our regular chem balancing equations, right? Make sure the same number of coppers on both sides, for example. And then charge is also conserved. So the charge on one side has to add up to the charge on the other. And if you use the half reaction method, the way the mini lesson showed you, you are able to cancel out the electrons, which proves that charge is balanced. All right, lastly, I wanted to touch on the mini lesson from Monday, equilibrium. So there are a lot of similarities between the BCA tables we use for stoichiometry and the ICE tables we use in equilibrium, but the differences are important, and these might be good to put on your one pager. For BCA table, everything has to be in moles. You can't do a BCA table if you are not in moles, whereas ICE tables, you can use molarities, which is moles per liter, or atmospheres if it's KP. In order to find what X is in your change box, you use the starting amount. So I just made this up, 4 moles, 1 mole, nothing, right? To find X, I'm going to take my before, 4, divided by the coefficient 2 to get 2. And then for oxygen, 1 mole divided by 1 is 1. The smaller is your X. Notice, though, that when I plug in X, we always move towards the zeros, whether it's BCA or ICE. So I'm moving towards the zero. So I'm going to use up these minus, and make this guy a plus. And then in my answers, I have 2 moles excess, so there's leftover of hydrogen, nothing left over, no moles of the oxygen, and 2 moles of the hydrogen. A thing that you can look for in a BCA table is these reactions are a one-way arrow. They're going to go to completion. So one of your reactants is going to end with 0. That's the limiting. That's the one that gave us the X. In ICE table, in order to find X, you need the K expression. And so I write the K expression. I always move towards the 0, so minus 2x, minus 1x, plus x. And then I just take I plus C to get E. So 4 minus 2x, 1 minus 1x, and then 0 plus 2x is 2x. And so I can plug in the equilibrium amounts. So 2x squared here, so 2x, and then squared because of this. 4 minus 2x, and then that's squared here, and then 1 minus 1x here. And if the K value is provided, then I can solve for X. Or they will give you another piece of information. It is possible that you might need to do stoich and then ICE, right, if we need to find a certain number of moles divided by total liters. But the idea holds true that you only put molarity or moles. Notice, though, once you solve for X, you can plug in, and you are going to have an equilibrium amount for reactants and products, whereas in BCA, one ran out completely. In equilibrium, you will have an amount of everything, even if it's really, really small. In this one, and one thing that I think was skimmed over a little in the video, not a big deal, I just want to hit on it. If they give you the K value, and they give you a starting amount of a product and a starting amount of both reactants, and we want equilibrium, that means they're giving me a number, and instead of this being 0, there's a starting amount. So how do we go about this? If we have a starting amount of everything, your first step is to figure out what direction the reaction is going, because if I have a number in all of my positions, we can't just say move towards the zeros. So we have to figure out, is this a forward reaction or is this a reverse reaction? To do that, we compare Q and K. So I'm going to use my Q expression, which is exactly the same as K. And really, this should say, I'm sorry, because these are ATM. This should be parentheses and say pressure, and pressure. So I'm going to plug in the starting values into my Q expression. It's Q because we're not at equilibrium yet. So I plug in and solve, and I get Q is equal to 5,000, or 5.0 times 10 to the third. And compare that to the provided K value, Q is larger than K. Times 10 to the third is bigger than 10 squared. So when Q is bigger than K, picture that on a number line, we have to move this way, which means we have a reverse reaction. So instead of my minuses being on this side, we are actually going to use up the HI minus 2x, and we're going to make these guys plus x plus x. So then I do my I plus c, so 1.0 times 10 to the negative second plus x, 5.0 times 10 to the negative third plus x, 5.0 times 10 to the negative 1 minus 2x. I plug those into my KP expression. They gave me KP, and I can solve for x. Unfortunately, KP is not small enough that I can omit the minus 2x and the plus x and plus x. So we have to do a quadratic, or you can plug it in your calculator. So I do the quadratic formula. I get negative 0.072 or 0.035. Well, the amount used up can't be negative, or the amount made can't be negative. So we use the positive option. And to find the equilibrium values, we're going to plug x into my equilibrium equation, or my equilibrium line, my E line of the ice table. So here's my E line for H2 at equilibrium. For I2 for HI, I plug in 0.035, and I get my equilibrium pressures. One thing to note, say like K was big enough, or small enough, I should say, times 10 to the negative fifth or smaller, the only x's we can omit. So say like we have this, x times 2.0 minus 2x. What if we have 1.0 plus x squared times x? So when we omit x's, because k is small, you are not allowed to omit x's that stand alone. So like this and this have to stay. This guy has to stay, or if it was a 2x. But we can omit this x, and I can omit this one because it's minus 2x, and I can omit this one, right? So just to be clear, when you omit using 5%, you cannot omit every single x value, but you can omit any x's that are being added or subtracted top or bottom. Hopefully that helps.